What if four equations could explain electricity, magnetism, radio waves, light, and wireless communication? In the 19th century, James Clerk Maxwell unified seemingly separate physical phenomena into a single theory. His equations became one of the greatest achievements in physics and the foundation of all modern RF engineering. By the mid-1800s, scientists had already discovered many electrical and magnetic phenomena. They knew that electric charges created electric fields, currents generated magnetic fields, and magnets exerted forces on surrounding objects. However, these observations existed as separate pieces of knowledge without a unified explanation. Engineers and physicists could describe individual effects, but they lacked a complete framework that connected them together. Questions remained unanswered. How exactly are electric and magnetic fields related? Why do changing fields seem to influence one another? And what mechanism allows energy to travel through empty space? The challenge was to find a mathematical theory capable of explaining all electromagnetic phenomena using a single set of principles. James Clerk Maxwell solved this challenge by developing four equations that unified electricity and magnetism into one elegant theory. Maxwell's equations are four fundamental equations that describe how electric fields, magnetic fields, electric charges, and electric currents interact. Together, they form the foundation of classical electromagnetism. The first equation explains how electric charges create electric fields. The second states that isolated magnetic charges do not exist, and that magnetic field lines always form continuous loops. The third shows that changing magnetic fields create electric fields, while the fourth reveals that changing electric fields create magnetic fields. The most revolutionary insight comes from the last two equations. They demonstrate that electric and magnetic fields can continuously generate one another. This self-sustaining interaction allows electromagnetic energy to propagate through space as a wave. Intuitively, imagine two interconnected systems continuously driving each other. When one changes, it causes the other to change as well. The second system then influences the first, creating an ongoing cycle. This is essentially how electric and magnetic fields interact. Physically, consider an antenna carrying an alternating current. The changing current generates a changing magnetic field. According to Maxwell's equations, that changing magnetic field creates a changing electric field. The changing electric field then creates another magnetic field, and the process continues outward through space. Mathematically, Maxwell's equations predict that these coupled fields travel as electromagnetic waves at a specific speed. Remarkably, this predicted speed matches the measured speed of light. Maxwell therefore concluded that light itself is an electromagnetic wave. Maxwell's equations are the foundation of all RF engineering. Every antenna, transmission line, microwave circuit, radar system, satellite link, and wireless communication network ultimately operates according to these equations. When engineers design antennas, they are solving electromagnetic field problems described by Maxwell's equations. When signals propagate through free space, waveguides, or transmission lines, their behavior is governed by the same principles. At the system level, Maxwell's equations explain radiation, propagation, reflection, refraction, polarization, impedance, and power flow. Nearly every advanced RF concept studied later can be traced directly back to this mathematical framework. Maxwell's equations are often considered one of the most successful scientific theories ever developed. They not only explained existing observations, but also predicted entirely new phenomena, including electromagnetic waves, long before they were experimentally verified. A common misconception is that RF engineers need to solve Maxwell's equations directly every day. In practice, many engineering tools and formulas are simplified versions derived from these equations. Even when not used explicitly, Maxwell's theory remains the foundation behind every RF design method. Now that we understand how electric and magnetic fields are connected, we are ready to explore one of the most important consequences of Maxwell's work. In the next lesson, we will study EM wave formation, and discover how changing fields create electromagnetic waves that carry energy and information through space. In this lesson, we learned that Maxwell's equations unify electricity and magnetism into a single theory and explain how electric and magnetic fields interact. We also saw how these equations predict electromagnetic waves and form the foundation of antennas, wireless communication, radar systems, and RF engineering. In the next lesson, we will explore EM wave formation and discover exactly how changing electric and magnetic fields combine to create waves that propagate through space. If you found this useful, like the video, subscribe, and follow for the next lesson.